Yesterday we looked at the unit circle and we found that it was helpful in determining the sine, cosine, and tangent, particularly of angles where we are rotating around a multiple of 90 degrees. So recall yesterday we looked at the x-coordinate on the unit circle is the cosine of the angle, the y-coordinate is the sine value, and then the ratio of the y over x is going to be the tangent of the angle as we rotate around the unit circle. So the sine of 90 degrees, rotate to 90 degrees. The y-coordinate is 1, so the sine of 90 degrees is 1. Rotate to 270 degrees. The x-coordinate for 270 degrees is located at 0, so the cosine of 270 degrees is 0. The tangent of 180 degrees, rotate 180 degrees. The tangent is the y-coordinate over the x-coordinate on the unit circle, and 0 over -1 will give us 1. Now we remember from FS that there were a lot of other angles that were responsible for knowing without a calculator. And we move down to the exact value of sine, cosine, and tangent to the reference triangles. Now recall that we had 3 reference triangles that we have to know. We have to know one for a 45-45-90 triangle, one for a 30-60-90 triangle, and we orient the 30-60-90 triangle in 2 different ways so that we can use one time the reference as 30 degrees and one time the reference of 60 degrees. So recall you need to know what the dimensions are, the relationship between the sides of a 45-45-90 triangle. And we know that for a 45-45-90 triangle that the legs will have the same length. And then we can always determine what the hypotenuse is with the Pythagorean theorem. Here is a convenient triangle to remember. If each leg is 1 unit long, then Pythagorean theorem would tell us that the hypotenuse has to be square root of 2. When we want to use a reference triangle, though, in the context of the unit circle, we really want this radius to be 1. And if I divide all 3 sides by the square root of 2, I can make a similar triangle that has this hypotenuse be 1 unit long, and therefore the legs will be 1 divided by the square root of 2, which we rationalize to become square root of 2 over 2. And that triangle should look familiar from FS. Now recall for a 30-60-90 triangle, we really want a triangle that has a hypotenuse of 1, but to remember how to draw that triangle and how to figure the relationship, it is convenient to remember that you always started with an equilateral triangle. Now the length that you let this equilateral triangle be would be up to you, but an easy one to work with is to have it be 2 units long. And if I drop a perpendicular down, equilateral triangles are also equiangular triangles. This altitude would bisect this lower side. So each of these legs of the 2 congruent right triangles would be 1. It would bisect this upper angle as well. Pythagorean theorem would allow us to figure out the altitude, which we would actually find would be square root of 3. And there's where we derive a single 30-60-90 triangle. Again, you didn't necessarily have to call this side 2. We just need to get the dimensional relationship between the sides of a 30-60-90 triangle. So if I move this triangle back down, that's where I got this triangle. Now once again, recall we want to plot this triangle into the unit circle approach, and so we want this leg to be 1, or this hypotenuse to be 1. So if I divide all these dimensions by 2, I get this resulting reference triangle. Those numbers of having a half for the altitude and having the square root of 3 over 2 for this adjacent leg to the 30-degree angle, with the hypotenuse being 1, should look familiar. So that would be the triangle that we'd use for our reference triangle when we're dealing with the unit circle. If I move and I look at the reference triangle, but I orient it so that this lower angle is 60 degrees, again, this is the typical triangle that we remember I have the hypotenuse being 1, and it can be plopped down into the unit circle approach so that I can develop what the sine, cosine, tangent is for any multiple of 60 degrees, any multiple of 30 degrees, any multiple of 45 degrees. So let's turn the page. Now, I'm going to actually start with the angles with the degree values first. We will go back up and look at the other two. However, we'll start with the angle of 210 degrees. So always draw a picture, and you can see that we're finding what the sine, cosine, and tangent of 210 degrees is. So I want to see where is 210 degrees. When I look at this, 210 degrees is going to have a rotation like so that is going to be in the third quadrant, and I am going to have a 30-degree reference angle. Recall, your reference angle is always the angle, the acute angle that your terminal side of the angle makes with the x-axis. So I have a reference angle here that is 30 degrees. Now I want to think of the unit circle as traveling around like so, and that this point on the terminal side of that 210-degree angle is located 1 unit away from the origin. And so now I can plop my little 30, 60, 90 reference triangle in there. You even made a scale diagram, I believe, in your FS class that you could actually pick up your little 30, 60, 90 triangle and plop it in position on your unit circle to see the relationship. Now, I do know that my x-coordinate is the cosine of that angle, the y-coordinate is the sine of that angle, and the tangent is the ratio of those two. So I know that my 30, 60, 90 triangle has my 30-degree angle here. Always remember, the side opposite the 30-degree angle is half the length of the hypotenuse. So this is going to be 1/2. Now, that y-coordinate is actually in the third quadrant, which means it is negative. This side is your x-coordinate. It is also negative, and that is going to be the negative square root of 3/2. So now I know that the x-coordinate for that point, if I rotate around the unit circle 210 degrees, the x-coordinate would be negative square root of 3/2. The y-coordinate would be negative 1/2. So the sine is going to be the y-coordinate, negative 1/2. The cosine is going to be negative square root of 3/2, which is the x-coordinate. And then the tangent, now we have a little bit of work to do with the tangent. We recall that the tangent is the y over the x. So if I take the y-coordinate divided by the x-coordinate, that ratio will give me the tangent of 210 degrees. I just have to clean it up. Negative 1/2 times 2 over negative square root of 3. The 2's will reduce, and I can see the negatives will cancel. And then I'm going to have to deal with rationalizing. And when I multiply, this becomes 1 over the square root of 3, which results in square root of 3/3. And it's a positive value because the y over x will be a positive value in that quadrant. Okay, now let's go back up. For the sine function, cosine function, tangent function, for an angle that is negative 2 pi over 3, we know that rotating in the negative direction is going to be rotating clockwise. And you can do a couple different things with this. You can transform that angle into degrees. Remember how we talked about pi over 3 is equivalent to 60 degrees, and I'm moving 2 rotations of pi over 3, so I'd be moving 60 degrees twice. So I know it's going to end up being over in my third quadrant again, with this angle being equivalent to negative 120 degrees. Now, this side goes on forever, but I'm going to think of it going out 1 unit. There's my reference angle with my reference triangle. And so I have to think, what is that reference angle? And I can see that my reference angle here is this little acute angle that it makes with the x-axis again. And that, again, is a 60-degree angle in the third quadrant. Now, that angle is 30 degrees. The 30-degree angle always has the side opposite that is 1/2 of the hypotenuse length. So I know that this side is 1/2, but it's negative because it's in the third quadrant. Therefore, this leg of the triangle is negative square root of 3/2. So I have to know my reference triangle for a 30, 60, 90 triangle. Now, once again, that's the x-coordinate, the negative 1/2. Y-coordinate is negative square root of 3/2. So when I find the sine of negative square root of 2, negative 2 pi over 3, I know the sine is the y-coordinate, which is negative square root of 3/2. The cosine of that angle is the x-coordinate, which is negative 1/2. And the tangent is going to be the ratio of those two, y over x. And when I take negative square root of 3/2 divided by negative 1/2, and when I invert and multiply, I'm going to end up getting square root of 3. And you'll start to develop some patterns of remembering what the tangent of a reference angle of 60 degrees is. And so the simplification will be something that will become easier to do as you move along. Now let's go to the other one. We have sine of 3 pi over 4. 3 pi over 4, we can think of rotating a couple different ways again. And I can think pi over 4 is moving 45 degrees. And I'm moving 45 degrees 3 times. So I'm moving once, twice, 3 times. So there's my 3 pi over 4 angle. You could literally convert it over to degrees and get 135 degrees. But I normally think of rotating pi over 4, which is equivalent to 45 degrees, 3 times, and do a motion of 45 degrees 3 times. I can see I want my radius of my point on the terminal side to be out 1 unit. I drop my perpendicular down, and I have a reference angle now that is 45 degrees. So now I want to visualize that 45, 45, 90 triangle plopped right here. I know that in a 45, 45, 90 triangle that these two legs have the same length. Now in this case, they are not going to be the same sign. The x-coordinate is negative square root of 2/2. The y-coordinate, being in the second quadrant, is positive square root of 2/2. The sine function has the y-coordinate being the value for the function. So the y-coordinate is square root of 2/2, so that is the sine of my angle. The cosine is the x-coordinate, negative square root of 2/2. And we can see what's going to happen with the tangent. We're going to be taking, once again, the y-coordinate, square root of 2/2, and dividing it by its opposite, negative square root of 2/2. And the ratio of those two is going to end up being negative 1. So now it's time to do some practice.